we're going to talk about what do you mean by linear in linear regression model, right? What is the difference between a simple linear regression model and multiple linear regression model? And what is the way of estimating parameters beta 1 and beta 2 in a linear regression model? So we'll use the ordinary least squares method in order to do that. Uh, so what do you mean by linearity? So when you talk about linearity, there are two things. One, it could be linearity in variables, and it could be linearity in parameters, right? It could be a linearity in variables, and it could also be a linearity in parameters. So what do we mean by this? Say, for example, we have yi is equal to beta 1 plus beta 2 xi plus ui. So this is linear in both parameters as well as in variables, no problem. Yi is equal to beta 1 plus beta 2 xi square plus ui. This guy is nonlinear in x. So this is, I mean, if you talk about linearity in variables, so this is nonlinear in x. Or yi is equal to beta 1 plus beta 2 1 upon xi, let's say, plus ui. This is also non-linear. So when you say linear, means the slope is same, that is constant. Linear in parameters. So it is del y, dy by dxi is just beta 2. What about this guy? Hmm? So it is 2 beta 2. What about this guy? It is beta 2, and this is x to the power minus 1. This is beta 2 upon xi square, right? Minus of beta 2 upon xi square, right? So these slopes are not constant, right? It's not a constant slope. So it is 2 beta 2 xi. Sorry, 2 beta 2 xi. These are not constant slopes. So this guy is linear in variables, definitely. But what we mean is not necessarily linear in, I mean, we don't have a problem as far as variables are linear, non-linear, doesn't matter. But what we have a problem is that parameters should be definitely linear, right? So the other interpretation is that you have yi is equal to beta 1 plus beta 2 xi plus ui. So you can estimate this, doesn't matter, as far as our estimation technique of ordinary least squares is concerned. But it will be, this is going to be a non-linear in parameters. This guy is non-linear in parameters. So when we say that we have a linear regression model, so what we mean is linear in parameters, not linear in variables. You can have explanatory variable non-linear as well, it doesn't matter. But what you definitely want is linear in parameters, right? You would definitely want linear in parameters. And what you are not suggesting is that you cannot estimate this model. You can definitely estimate this model. There are nonlinear techniques to estimate this model, and you might even get better estimates using nonlinear techniques. But that's the part of the advanced econometrics, not the introductory part. So when what we are talking about is just the introduction, where when the moment we say linear in parameters, what we mean is in terms of beta 1, beta 2. Xi's can take any form, whatever. The second thing is, what do we mean by a linear model or a simple linear model and a multiple linear regression? So, a simple linear regression, and here you have a multiple linear regression. So, simple linear regression is just this, that yi is dependent only on one variable. Now, beta. So your CBSE class 12 scores are dependent upon annual family income. But that's not necessarily true. It can also depend upon many other things apart from just annual family income. Because in case if that would have been the case, then only the people only wards of rich people would be getting very high marks. But that's not necessarily true. So it also depend upon your inert capacity. So you have not taken up any variable depending on that. But supposedly if you take up some other variables also, beta 3, beta 2 x2i, beta 3 x3i plus ui. So for a multiple linear regression model, it means there is one more variable, at least one more variable, just one variable in the model. So, for example, your score in CBSE class 12 is not only dependent upon the annual family income, but number of tuitions which you have taken, right? That also could be one of the reasons which can affect your score. So, multiple linear regression is that not only one variable, but more than one variable is affecting the dependent variable. That is what multiple linear regression models. Now we come to the most important part of the recording, right? Which is how do you estimate the parameters? That is the method of ordinary least squares. The method of ordinary least squares. Okay. So what do we want to do is that how is it? I mean, how nicely sample regression function is estimating the population regression function or is showing population regression function, right? That is that uh, is a good estimate of the sample, or sorry, of the population regression function. That's what we need to know, right? Whether your estimated PRF. So what is estimated population regression function? Nothing but sample regression function. That is sample regression function, because you do not have the entire population with you. You just have the sample with you. Is a good estimate. Is a good estimate of true population regression function, right? Right. So, and other thing is that how do we estimate this population regression function? So the first question is, how do we estimate this population regression function? That is, how do we find out the sample regression function? This is what we're going to answer, and in this thing, in this recording, we'll talk about this thing later. That is whether the sample regression function which you have calculated is that a good estimate or not. That's whether it is good or not. We'll talk about it later. But how do you estimate it? So there are many methods of finding out the estimated PRF, that is your sample regression function. We're taking up the one which is ordinary least squares. Uh, and this is the method of ordinary least squares. Well, your two variable population regression function is what? Yi equals to beta 1 plus beta 2 xi plus ui. That is your population regression function. This is not directly observable. PRF is not directly observable because beta 1, beta 2s, they are not known, right? And you don't have the entire data for the entire population with you. So you estimate it from your sample regression function. So what do you have? You have yi hat plus ei, that is equal to actual y. And what is yi hat? That is beta 1 hat plus beta 2 hat xi. So beta 1 hat and beta 2 hat, they are the estimators of beta 1 and beta 2, right? And ei is the residual. I hope you remember that. Hmm. So this guy is the residual, and you can, I mean, in very loosely speaking, an estimate of the error term out here. Hmm. So what is your residual? Actual y minus estimated y. So estimated y is yi hat, which is beta 1 hat plus beta 2 hat xi, beta 2 hat xi, right? So what are these residuals? They are the difference between the actual y and the estimated y. And you need to choose beta 1 hat and beta 2 hat in such a way so that the residual sum of squares is minimized. That's an idea. So choose beta 1 hat and beta 2 hat, right, in such a way that the residuals ei are as small as possible. Are as small as possible, right? And OLS says this, that beta 1 hat, beta 2 hat should be found out in such a way that the residual sum of squares, RSS, summation of EI square, is as small as possible. Why are we minimizing the sum of square of errors and not just the errors? There are two reasons behind this. One, when you minimize the sum of squares of errors, so one thing which it does is that it removes the sign of the error. So minus one, I mean, for example, your actual value was 2, uh, and the error is, and estimated value is 0. So the error is plus 2. Okay. Now, actual value is minus 2, uh, and the estimated value is 0. So the difference is minus 2, right? The idea is that the sign of the error, that problem is eliminated with this, right? So, so it removes the sign of the error. Mm. And hence treats positive, negative errors alike. First thing, right? Other thing, I mean, when you square the errors, it has a tendency that it will penalize the large errors more. I'll give you an example. So let me just write this first. Squaring the error has the property of penalizing the large errors. For example, I mean, you have estimated beta 1 hat and beta 2 hat, right? You have estimated beta 1 hat and beta 2 hat, and the residuals were coming out to be 1, 2, minus 1, minus 2. These were the residuals which were coming. Fair enough. And then for the another choice, I mean, the residuals were coming out to be minus 1, minus 1, minus 1, and 3. Something like this, right? What is the absolute sum here? Uh, Absolute sum here, 2 plus 1, 3, minus 2, minus 1, 3, minus 3, that is 0. That's an absolute sum. Here also the absolute sum. So absolute sum is same for both of them. Fair enough. What about the square? 1 square, 2 square, 1 square, 2 square. So it is what? 10. In this case, 1 square, 1 square, 1 square, 3 square. In this case, 12. In the second case, yes, one of the error has reduced in a way. From 2 to minus 1, it has come like this. But one of the error has gone like very large, 3. So since you have a large error, squaring the error has penalized this case more than the earlier one. You got an idea? So when you have squared the error, it has penalized this scenario more than the earlier one, and that's what you want. So if you run the regression with this or this, so it will give you a better fit with this as compared to this. That's an idea, right? So that's an idea. Are you with me? So it is putting a more penalty on the second one than the first one. Right? So it has put the large penalty here, large penalty here, large penalty on the large error. And that's a very wrong English. It should be heavy penalty on large error. How do you know this? I mean, you got the penalty in terms of 9 out here. That's an idea. So this is the reason you square the error and then you minimize it instead of just minimizing the absolute sum. Okay. So what do we have? We have summation of ei square, summation of yi minus yi hat ka square. That is summation of yi minus beta 1 hat minus beta 2 hat xi ka square. That's what you do. So you need to choose some such beta 1 hat and beta 2 hat which is going to minimize this error sum of square, so residual sum of square. So what do you do? Uh, for what you're going to do is We'll be minimizing this. So when you minimize this with respect to beta 1 hat, this is going to be minus 1 out here. Now you're minimizing this with respect to beta 2 hat. So it is going to be xi, and with this also has a minus sign out here. So I'll put it like this. Is this right, beta? So this minus 2 going there, it will become what? Summation yi. Okay, I'll write it slowly. Okay, I'll write it slowly. Summation yi minus beta 1 hat minus beta 2 hat xi equals to 0. That's what it is. So you can write it like this: summation of yi minus n beta 1 hat, because there are n terms out here. And what is the uh, sum of a constant for n terms? It will be n beta 1 hat. It's a simple statistical rule. Beta 2 hat being a constant will come out of the summation sign. Right, beta? It is like this. So I can write this as summation of yi equals to n beta 1 hat plus beta 2 hat summation of xi. What about this guy? This minus 2 is going there, and this xi is going to be multiplied. So it should be yi xi minus beta 1 hat xi square. No, beta 1 hat xi. So sorry. Beta 2 hat xi square equals to 0. So basically what you have is this guy. Summation of yi xi is equal to beta 1 hat summation of xi, because beta 1 hat will come out of the summation sign being a constant, plus beta 2 hat summation of xi square. Now it up. So these are your first and second. First and second, like this. So I can write this in the matrix form. So what do you have? Okay, how do I write this? N summation xi summation xi summation xi square beta 1 hat beta 2 hat summation yi summation of yi xi. Now beta. So you'll have like this, and I hope that all of you know how to use Kramer's rule, because we need to get the value for beta 1 hat and beta 2 hat. So using Kramer's rule, when I want to find out beta 2 hat, what will I do? I'll superimpose this column onto the second column of this coefficient matrix, right? So what will I do? So my first column will remain same. And my second column will become this. Now, beta, I've superimposed this column onto the second column of this. Upon the determinant of this coefficient matrix. Upon determinant of this coefficient matrix. So determinant of this augmented matrix upon determinant of this coefficient matrix. What will this be? N summation xi minus summation of xi summation of yi whole upon n summation xi square minus summation of xi ka whole square, summation of xi ka whole square, right beta? This is what my beta 2 hat is. This is going to be my beta 2 hat. Acha, tell me one thing. Can I also um, write it like this? Can I also write it like this? Beta 2 hat summation of small xi yi upon summation of small xi square. Now, what is a small xi? So these are some of small xi's are deviations of xi from its mean. Small y is deviation of yi from its mean. What will this be, beta? In place of small xi, what will I write? Xi minus x bar. In place of small yi, what will I write? Yi minus y bar. I can write like this. I'll tell you how are these two equal. In place of small xi, I can write xi minus x bar ka whole square. Now let us look at how is this beta 2 hat is similar to this guy. So let me look at the numerator first, right? So summation of xi minus x bar yi minus y bar. So let me just write it properly first. Xi yi minus y bar x by xi minus x bar yi plus x bar y bar. Plus n x bar y bar. हाँ बेटा, I hope you know this, that summation of xi upon n is x bar and summation of yi upon n is y bar. So in place of summation of xi, I can write what? Nx bar. In place of summation of yi, I can write what? Ny bar. And this is what? Nx bar y bar. हाँ बेटा. So you have what? Nx bar y bar and यहाँ पे minus nx bar y bar. It will get cancelled out. And you'll be left out with what? Summation of capital Xi yi minus nx bar y bar. Like this. So this n and n will get cancelled out. And this is n summation xi yi minus summation xi yi. I mean, this is whole upon n. Just wait for a while. Just wait for a while because this will get cancelled later on. But if you look at the numerator of this, this looks like this guy only. Okay. Now let me look at the denominator here. This guy, summation of capital Xi minus x bar ka square, xi square plus x bar square to xi minus x bar, right? So it is summation of capital Xi square. This will be just n x bar square because it's just a constant now, minus 2x bar will come out of the summation sign into summation xi. Now beta. In place of summation xi, what is x bar? Summation of xi upon it. So what is summation of xi? N x bar. So it is this is nx bar square. Nx bar square minus 2 nx bar square. So this is what? Summation of capital Xi square minus n x bar square, like this. You with me? Minus n x bar square. I can write like this. Now if you just look at uh, the the uh, denominator of that, okay, now can I also write it like this? In place of x bar, can I write summation of capital Xi upon n, iska square? So this is going to be what? Summation of capital Xi square So this is going to be what? हाँ बेटा. So now if you look at the numerator denominator, so let me just write the numerator denominator again for this. This numerator, this guy, minus summation of this guy is the numerator upon the denominator. So this thing will get cancelled out. And this is the same thing, beta. This is the same thing here, right? And you have got this thing from what? Xi minus x bar, yi minus y bar upon xi minus x bar ka square, and which you can also write as summation of small xi small yi upon summation of small xi square. This is what you can write. So this is what your beta 2 hat is. Beta 2 hat is. Oh my god. Okay. Beta 2 hat is. Just look at this expression, beta. This is your first one, na? Your let me just write. This was your first expression. So can I write it like this? Summation of yi equals to n beta 1 hat plus beta 2 hat summation capital Xi. Yes, I can write. Can I divide both the sides by n? I can divide. What is it that I'll get? Y bar equals to beta 1 hat plus beta 2 hat x bar. This is what you'll be getting. So what is going to be your beta 1 hat? That will be y bar minus beta 2 hat x bar. And this beta 2 hat is what? You have just derived summation of small xi by I upon summation of small xi square. This is what you have. Huh? So I'm going to stop out here because I'll talk about the properties of these estimators tomorrow. And what I'll be doing, so what is it that you have learned in this recording is, what do you mean by linear in linear regression model? What is the simple difference between the simple linear regression model and the multiple linear regression model? And what is the way of estimating beta 1 hat and beta 2 hat using ordinary least squares? And why do you minimize the uh, error sum of squares? That is sum of squares of the residuals and not just the residuals. That's what you have learned, right? Okay. Thank you, beta.